All right, so it's Thursday morning, and I've been doing a lot of work on looking at my design in relation to other designs that purport to do similar functions. And this all started when we left off. I was going to be working on the software, and then you're really driving this towards the finished product. And I thought about writing this up in a magazine article, and so I looked at, what other people have done in a similar fashion. And I found that there are a lot of people that have written up GPS disciplined oscillators and variable frequency oscillators, both in the magazine and on the web. There are a lot of projects. And, I've seen stuff on eBay that does this, and stuff's, a whole lot cheaper than what I'm doing. And so it gave me some concern about, is my approach actually a good approach? Am I making it overly complicated, spending too much money, and so forth? So I spent, instead of working on software, looking at contemporary or related designs. And so the first thing I looked at, and this is similar to the approach that's in the magazine, is what's done in this QCX Plus transceiver. And this is a device for Moore's code. It's 50 watts, and this has a GPS in it. And I've added some LEDs, and also has a VFO function, which I've pinned out on these SMAs. So let's look at, it's not this particular design, but it's very similar to what you find out there in the literature. And basically what you have is the synth board, and this is the one that I'm using, but this has the crystal on it still. And so this is running, and they use it to generate a 2.5 megahertz signal that gets fed into the Arduino. The Arduino can't, it's 16 megahertz inside. I think you have to have the fastest timer you can run off of that is probably 6 megahertz. So they divide it down, and they start and stop the timer based upon an interrupt, which comes from the GPS and its pulse per second signal. What they do is they get the PPS comes in, and they start the counter. It's an interrupt, so there's a software loop in there, and they count 40 seconds, and then they stop the counter and look at the residue. And it's a 16-bit residue, and so they don't have the full count, they just have part of it, which is sort of what I do. And so they have expect 10 million counts. They can figure out how many they have. They have 10 million and 7 counts. They know they can calculate what the speed of this crystal is, and then from that they can use the M and the D's to correct that when they subsequently make whatever frequency they want to make. And so if you want to make 10 megahertz exactly, you can find multiplier divider values that will work for this. Unfortunately, the actual operation of the chip, if you put in weird values for the fractional part, you'll get some jitter effects, which I'll show you. And then since the math in there is only, basically what they're doing is in my calculations, my multiplicative factor is based upon what the reference is, but they've measured what the reference is, and so when they do their calculation, instead of being 10 megahertz, they calculate it using 10 point blah blah blah, 15 hertz, and so you get a weird fractional value for M, and you may not be able to represent that in the 20 bits in the math. So the value that they actually get, you might not be able to set it exactly, and it's going to have those artifacts. But in the context of that device, it's fine. The VFO, it's only within 10 hertz, and you can certainly do that. And this device will clean up some of that edge jitter if it's not too bad. And so it's actually an effective solution, but not as good as what can be done with a real oscillator running at 10 megahertz. But it's certainly cheap. This is a $20 processor and a $5 board, and you get a value which is probably going to be within a hertz or half a hertz of what you actually set it to. So it's a good solution, but not good enough for the frequency measurement test. The other method is used by this, which is the Bodnar, and that I've been saying it wrong. Oh yeah, yeah, it's Bodnar. And that this has the GPS, and then it has two outputs, and what's in there, and that's the thing that I've been I've been testing myself against and comparing myself against, and what they do is this: they have a GPS receiver, which instead of having a PPS, has a time pulse, which you can set in their GUI to whatever value you want, and that goes into the Silicon Labs chip, and that gives them the two outputs. And so actually that's this device right here. And so this is the module for the GPS. So I have the GPS, and that's the antenna, and I'm looking at the time pulse out. And so you say, great, instead of doing all the hard work that I'm doing in trying to get a 10 megahertz signal, you can just have that do all the work for you. So I, set it up, and here's 10 megahertz coming out. And it is 10 megahertz, but it's not perfect 10 megahertz, unfortunately. There you go. What it does, and so here's this phase shift, or this jitter that you see. And if I zoom out, you can see it's pretty bad. It's always a consistent, 16 nanoseconds. But as a frequency reference, that's not very good. Certainly your PLL will attenuate some of that, but I wouldn't be relying on that in a high precision system. Again, that's going, I'm measuring this directly with the radio. In this application, this goes into the frequency synthesizer that they have, and at lower frequencies you don't really care, but at high frequencies that I'm interested in, it is an issue. If I change it to a value, I'm working on the PC, if I change it to a value that's 1 megahertz, 1 megahertz, for instance, there's no edge artifacts. So actually, with a 1 megahertz signal, it's nice and solid. So I like that. What happens is internally in the GPS unit, it has a 64 megahertz internal rate. And so it can place an edge every 15 nanoseconds, and that's what it does. So when it wants, so if you tell it to give me, 1 megahertz, it counts 64 and makes your edge. If you want to do 10 megahertz, well, you can't, it doesn't divide evenly, so they have to do something tricky where they, count, 7, then 6, then 6, 7, 6, 7, 6, 6. They do this pattern, and, this number of edges, 4, 7 edges and 6 edges gives you 64 edges total. So this pattern repeats, and so that's why you see that jitter or that phase shift in the edges, because that's how they do the synthesis. And so no matter, powers of 2, it's clean, but if you give it basically any frequency, you're going to see these edges being jittered that way. And that's inside the U-Blocks chip. That's what's coming out. So in the application inside that Bodnar box, this jittery 10 megahertz, actually it's this weird value, I measured it. This jittery value comes into that chip, and it gets synthesized from that. And so again, this device will filter out some of that jitter, and your output, should be clean. So again, this is a really good solution, and I'm going to actually explore it some more. What I'm going to do is, I don't like the 10 megahertz being junky, but the 1 megahertz is clean, so I'm going to actually put that through a PLL, and I'm using, unfortunately, there's this older style CMOS device that basically has a VCO and it has a phase comparator. So what you want to do is, you have 1 megahertz come in, and it's going to compare it to a second input, and that is an out, and I'm comparing it to the output of the PLL divided by 10. So if the VCO inside is going 10 megahertz, because that's what I want, I'm going to divide that down by 10 before putting it back into the PLL so we can compare it to the 1 megahertz. And this is how frequency synthesizers actually work, because if I had a divide by 2 over here, then this would be comparing it to 10 over 2, so I get 5 megahertz out of here. So this should clean up this nasty jitter, although the VCO inside here may or may not be completely stable, but it's a PLL, and I'll for sure get 10 megahertz out. I'm not sure how much noise I'll have. And again, for frequency synthesis purposes in the frequency measurement test, that's probably okay, because if I want 14 point whatever megahertz coming out of this device, I'll get that, and that's what I use for the FMT. But for clocking the radio, if I really want a perfect 10 megahertz, this might not be as good. So I'm going to look at that, and again, just doing some research and some testing, and it's lots of fun. I then thought about, well, okay, so then what are the intrinsic issues with any of these solutions? And so the QCX solution uses a TC EXO, and the Bodnar does also. And so if you look at all their specs, the stabilities are in the order of 0.2 ppm over temperature over whatever. And so at worst you can say this is a 0.2 ppm device, and that's going to be for instance, a QCX every 40 seconds it calculates what that crystal is. Well, in the meantime, it could potentially have moved around and shifted by as much as 0.2 ppm. That's in the extreme. The crystal I'm using, this oven oscillator, so the other one is a temperature compensated. This one actually has an oven in it, so it's always at the same temperature. That one is in, the worst case, I'm using this one. It's 10 parts per billion. So it's, 20 times more stable over its entire range. The other advantage is it's nominally within less than a part per million of 10 megahertz, and I know just from looking that if I set the adjustment in the middle point for the frequency change, that it's within 0.1 or 0.01 parts per million. So just even turning it on without a GPS, it's 10 times better than the other solution. On the super far end is the rubidium oscillator, which is an atomic clock basically, and that it's tunable also, believe it or not. It's 10 megahertz, and it is plus or minus 1 part per billion. So it's it's generally and then actually the frequency pull is plus or minus 5 parts per billion, whereas the oven oscillator, it's plus or minus 700 parts per billion. So the tuning on this, it's 100 times smaller change, and the stability is easily 100 times better. But it's an atomic clock, so what do you expect? The other thing, so I'm trying to make my system better, and so the way I'm doing that is by two things. One of them is, okay, I didn't realize I had a pause function, so that's going to come in handy in the future. So what I want to do is actually, when I'm tuning the system, I usually find that I'm jogging between two values, and so I can get very, very close to being exact, but I want some more granularity. And so one of the things is right now the DAC count, one DAC count is 1 millivolt, and that's the finest I can go. And I usually at most use, the most I've ever tuned it was probably, over a range of maybe 20 or 50 of those counts. And so what I want to do is I want to make a count be worth more. And so I broke out SPICE, which is a circuit simulator, And this is a circuit that, this represents the range of DAC values. So it's, nominally around 2.5 plus or minus 2 volts. And I want to actually make the output be smaller than that. I want it to be still around 2.5 volts, but maybe have it be, plus or minus half a volt or a tenth of a volt, something like that. And so what the circuit is, this is an op amp. It's a follower. So whatever voltage comes in here, you get the same voltage out there minus the details of the circuit here. And what I have here is a circuit that generates a voltage offset. So this is the signal from the DAC, and I reduce it by some amount, and that produces a current. To that current, I add the current from this voltage source, which is through a trim pot, and these two currents get added, and the corresponding voltage is the sum of those. So this is the offset, and then this is the variable value. And I can't just divide it down, because if I do that, my DC level will be wrong. So, and this is actually the first time maybe I've used SPICE in at least 20 years, if not since grad school. So this is what the sim looks like. Centered around 2.5. I have a plus and minus 2 volt swing, which is what the DAC can do. And when the signal comes out of this voltage divider, that's this V reduced, that voltage swings around, what is that, 1.55 volts, and has a small offset like I want it, or small swing like I want it to have. And then this curve over here, this is the output of the op amp, and so it's not quite centered at 2.5, but that's why I have the trim pot. But what it shows is I can take a big swing from the DAC and turn it into a small swing. And so this is, I think it's a 10 to 1 reduction. It might be a 10 to 1 reduction. And so I can tune by, 100 microvolts in the system. And of course you ask yourself, well, 100 microvolts, that's noise level, which is true. And so I'm going to be working at the same time on cleaning up the power supplies. And so I got a bunch of inductors, and so I'll be using those to filter. Generally, the power rails are 200 millivolts of noise at 10 megahertz frequencies, which is what you would expect from the oscillators and the synth chip. And I can get that down to 50 millivolts, which is running into the noise floor of my scope. So I'm feeling pretty good about that. The other thing, and actually, regardless of the noise or whatever, the OCXO, and I'll filter that also and have a cap there. Inside the OCXO, it can attenuate that noise also. So if you get a lot of noise, the OCXO adjusts slowly and certainly well below the frequency of the noise coming in there. That's why, even though, again, with 200 millivolts of noise in the whole power supply system, I can still see a difference on a DAC count of 1 millivolt. I expect that I'll see a difference in the DAC count when I reduce it. And 10 to 1 might be too extreme, but that's probably okay. I'd rather have it be, I tune it and I don't really see anything till I go up or down a couple counts. That's better than throwing away fine-tuning ability. The other thing I've been working on is sort of a naive tuning algorithm, and so this is a hybrid of the way I was thinking about it before and with the more tuning, but there'll be some phases, and they'll be in the display. So the first phase will be a warming up phase, and so the frequency is jumping around. It hasn't been stabilized. I don't do anything. I'll get into a course adjustment where I can adjust by 100 counts, which is what I do with those buttons right now, and I can use that. It'll come up 1 or 2 slips every second, and I use that to get it to within 1 slip a second. I'll switch to a medium, and there I adjust by 10 to get the count to 0, some amount of seconds. So this is in the regime where it doesn't slip most of the time, but it occasionally does a +1, which is where that ongoing counter comes in. And then there'll be a fine adjustment. It's basically what I do also by hand, where I can adjust by 1 to get at least 50 seconds or so without a slip. And then once I'm in that, I can do the superfine where I look at what the phase is, the phase position, and I balance the rate. Because when I'm at better than a slip every 50 counts, I can still see that edge walking across. And so just looking at that, when I do it by hand, if I see it moving that way, I make it slower. If I see it moving to the right, I go and I make it faster. And that'll be the fine and the superfine phase. And there has to be some hysteresis, built in so that, this does sometimes jump back and forth. I mean, ultimately when it's stable, sometimes it alternates between two values. Well, you don't want to do anything until it goes, if it's going between 3 and 4, you don't want to do anything until it goes to 5. Then you send it back, and then so that just takes it puts some hysteresis in the system. So I've been paying attention to what I do manually. I'm going to put that into an algorithm. And like I talked about before, I'll first probably just have it say what phase it thinks it's in and what it wants to do, just so I can I can look at it right now and say, well, I would hit +1 twice and see what it tells me. So that's the next step. Do the DAC reduction, redesign that top part with the extra filtering circuits, and try out the PLL on that GPS unit. So initially, again, a week ago, I was feeling like, oh man, I'm overthinking it. But then, digging into the details, it turns out that, I'm getting that, those last digits of precision and accuracy on my frequency, which, in the end, it's going to be lost in Doppler shift noise for the frequency measurement test. But the exercise here is to produce, the best frequency reference signal that I can. And so I'm already better than the software method, probably going to be better than the Bodnar, and learning a whole lot and having a lot of fun figuring this stuff out. So that's where things stand. Maybe it's a lot of work, a lot of hardware work to be done, but maybe have an update next week sometime. All right, thanks for watching.